Welcome back everyone. So let us go to the next theorem for this chapter. Okay, so we have done differentiability now. We have defined differentiability. We have seen some examples on differentiability. So the next question which arises is based on experience of one variable calculus is that every differentiable function is continuous. Okay, so can we say that every two variable or multivariable function which is differentiable is also continuous? Okay, so now that result is true, but we require some tools to prove it. Okay, so same way, when we are done in one variable calculus, we had done a theorem called Carathéodory's lemma. Okay, using Carathéodory's lemma, then we just prove that every differentiable function is continuous. Okay, I think so this name Carathéodory's lemma is not used in Bartle's book, huh? But anyways, I'll state the result and then I'll go to the new lemma over here for two variables. Okay, so the lemma for two variables is called an increment lemma, in which we describe something called increment functions. Okay, so using this result, we will prove that every differentiable function is continuous. Okay, so let us start now with the results. So the first thing is Carathéodory's lemma. I'll state this result, you will recognize it after I state it. Carathéodory's lemma. Okay, the result is let f oh wait let D be a subset of R, D be a subset of R, C be an interior point of, and let C be an interior point of D. Okay, then if D to R is differentiable at C if and only if there exists a function there exists a function f1 and D to R such that f of x minus f of c f of x for all x belonging to D, for all x belonging to D. Okay, for all x belong to D, and f1 is continuous at C. Okay, f1 is continuous at C. Moreover, if this conditions hold, if this conditions hold, then f prime of c f prime of c is equal to f1 of c. Okay, is equal to f1 of c. Just let me rub this out. Okay, f1 of c. So yeah, so this result is covered in Bartle's book without this name theory. Okay, yeah. So now what it says is that a function is differentiable if and only if you can find a continuous function f1 such that f of x minus f of c, okay, divided is equal to x minus c into f1 of x. Okay, so this thing is not so difficult to look into why the result is true. Okay, if we just take x minus c down and take limit x tending to c, the LHS turns out to be the derivative of this. Okay, LHS turns out to be derivative of f of x at c, f prime of c it will become, and this becomes f1 of c on the RHS. Okay, so because of that this conclusion comes. Okay, so there are little steps involved in this proof. If you want to see the detailed proof, you can click on the I button which is coming on top of your screen over here. Okay, yeah, that will give you the link to the proof for the uh, Carathéodory's lemma which I had covered for the first year students. Okay, so now similar to this condition, let us try to make a condition for two variables now. Okay, so this condition for two variables is called as a increment lemma. Okay, so let us write down. I think so there's a lot of thing on my pad here, that's why this thing is getting a bit bad handwriting. Because of this moisture, this pad has become a little greasy. Just hold on, let me rub this out. Okay, little better now. Increment lemma. Okay, so let me write down the statement for this result. Same as how the previous one was. Let D be a subset of R2. Let end over here. Small l, and let x naught y naught be an interior point interior point of D. Then f from D to R, but this time D is a subset of R2. Okay, just R, D to R. Yeah, D to R is differentiable. D is a subset of R2. The codomain will be R here. Okay, is differentiable. Is differentiable at x0 y0 if and only if there exists we have two variables now, so we require two functions. There exist functions f1 of x. Wait, I'll write both the functions first. f2 from D to R. Okay, there exist functions f1, f2 from D to R such that f1 and f2 are continuous at x0, y0, such that f1, f2 are continuous at x0, y0. And this difference f of xy minus f of x naught y naught this is equal to okay, same as last time, but since there are two variables now, we have added a term for the second variable, and this is true for all x belonging to, for all xy belonging to D. Okay, moreover, just like last time, moreover, if these conditions hold, then gradient of f at x naught y naught is nothing but I'm not supposed to give you the spoilers first only, right? So yeah, okay, so the gradient of f turns out to be this functions f1 and f2 at x0, y0 over there. But what was gradient of f actually supposed to be? It was supposed to be the partial derivative of x with respect to partial derivative with respect to x at x0, y0 and partial derivative of y with respect to x0, y with respect to y at x0, y0. Okay, but that over here I have written it as f1 and f2. So what do you know now? f1 of x0, y0 is nothing but partial derivative of f with respect to x0, y0, and f2 is nothing at x0, y0, only at x0, y0. We can't say at other places. unless we know that the function is differentiable at those other places, right? So f2 of x naught y naught is equal to fy x naught y naught. Okay, partial derivative with respect to y. Okay, so let us start with the proof. Okay, proof. Let us start with the differentiability condition first. Assume that f from D to R is differentiable at x naught y naught. Okay, is differentiable at x naught y naught. Then what do we know? Then there exists alpha 1, alpha 2 belonging to R such that, or you can actually do this, alpha 1, alpha 2 belong to R2 such that limit of just note, I'll make a change here in the definition, fxy f of x naught y naught, right? Now instead of writing h times alpha 1, I'll replace my h with x minus x naught. Okay, alpha 1 and y minus y naught into alpha 2. Okay, so basically what I've done, I've put h is equal to x minus x naught, k is equal to y minus y naught. I've not done anything new. Well, I've done this many times when you are loading one variable differentiation. Okay, this is a normal trick of replacing h with x minus x naught. Okay, yeah, so denominator was h square k square, right? So that will have to be replaced by x minus x naught y minus y naught the whole square. Okay, and this entire thing will be equal to 0, but here the trouble is, what is the limit tending to? We had h tending to 0, but h we have replaced with x minus x naught, right? So in this case, the limit will have to tend to xy tending to x naught y naught. Okay, okay, so this is the definition which I have just used. So what I'll do now, for sake of simplicity, because I have to do a lot of simplifications here, I'll just rename the numerator. This numerator term, I'll give it a new name. I'll call this numerator fellows xy, f of xy. I'll define it as okay, we'll just say define now. Define f of xy small f xy minus f of x naught y naught minus x naught alpha 1 minus y naught y1. It's just y. Okay, so this is the expression. We'll call this as f. Yeah, for many practical purposes, no, I'll be using, yeah, we'll just give a name to this expression first. Yeah, call this as put this in a box. It's the first equation for us. We'll call it as 1. Okay, I'll modify this equation a little bit and I'll write it like this: f of x, y I want my final answer to be the difference of these two terms, right? So that's why wait, I'll write this term first. X minus x naught alpha 1 plus y minus y naught alpha 2. So in other words, I've just taken this terms on the other side. Okay, I'll mark this also as 2. I could have called it 1 dash, but let it be 2. Okay, I'll be using this version of this expression at some places. So that's why I'm giving it this name to it. Okay, so we're done with this. So now we'll define the functions. We'll define the functions. Okay, one more thing I need to tell you is this notation. One thing which follows from this is hence limit of x comma y tending to x naught y naught of f of xy root over okay. So this you get. Okay, so this I'll call it as 3. Okay, all this done inside. Now let us go further to define the functions. So this is something what we call as proof by construction. So we construct the functions, we construct the required sets or something according to our need, and then we prove that that set works. Okay, so just like how you have proof by contradiction, proof by induction, right? There's something else called proof by construction, where you construct the things which you require and then you show that they work, and hence the proof is true. Okay, so now in this case I'll be constructing the functions f1 and f2, then I'll show that those f1 and f2 which I constructed, they'll satisfy the requirements for the theorem, and hence the result is true. Okay, so let's move on towards defining f1 and f2. Okay, so define f1 f2 from D to R. These are two variable functions, huh? Okay, because D is a subset of R2. Okay, as follows. Okay, so what are they to be defined as? f1 of x comma y is going to be defined as alpha 1 and alpha 1 plus a big expression okay. So this is defined as alpha 1 when x comma y is equal to x naught y naught, and here you have x comma y is not equal to x naught y naught. So this is the function f1. It has been artificially defined as follows. Okay, there's no other logic behind that. It has been purposely done so that it works now. Okay, that's how proofs by construction works, that you artificially create a function, okay, which satisfies the requirements of your theorem. Okay, so this being said, observe that that's a constant value alpha 1, okay, at x is equal to x naught, xy is equal to x naught y naught. It takes this value alpha 1 plus some thing big of at other points. Okay, so we'll have to show that this function is continuous after some time. Okay, that's going to be one of our tasks, right? Next we'll be defining alpha 2 f2 as follows. Do the same thing, but instead of alpha 1 just write alpha 2. Where there is x you have to put y also. f2 of xy alpha 2 plus y minus y naught okay, same like last time. Xy is equal to x naught y naught, and here xy okay. So this is the condition. Oh yeah, so f2 has been defined like this, just like last time, but the values have been changed. Okay, so my task is now to show that these two functions which I have written down here actually satisfy what I have required. So the conditions in the theorem and the fact that f1 and f2 should be continuous. What is the condition in the theorem? The condition in the theorem, just read the statement over there, that this f1 and f2 have to satisfy this equality over here, that f of xy minus f of x naught y naught should be equal to this. Okay, clear? So we have to do this. Okay, page got over. Not even 1/3 of the theorem is over. Okay, never mind. Okay, so let me write here. So go to the next part of the theorem to show that they satisfy this condition. Okay, so I'll start with the RHS of that expression. Okay, for write down for x comma y not equal to x naught y naught, we have okay. So when x is not equal to this, okay, so this is the RHS, this is equal to, there's a big expression here. Okay, so anyways, I can move to the left of my screen. I don't know about you all. Okay, you will have to write this on the next line. Okay, so x minus x naught times f1 of xy. What you will get? That expression over there is equal to, what is f1 of xy? It is, wait, let me write this. It is equal to alpha plus capital F divided by the square root, no, sorry, not square root, the x minus x naught the whole square and y minus y naught the whole square. On numerator there is one more term there. Okay, yeah, anyways, this is alpha 1 plus, there is already an x minus x naught in the expression over there in the numerator, so this will become x minus x naught the whole square of f of xy. Okay, I have just substituted the values of f1 of xy. Okay, y minus y naught the whole square. Okay, same thing repeat with f2. So this will become y minus y naught alpha 2 plus, there is already a y minus y naught in the numerator there, so this will become y minus y naught the whole square f of xy upon x naught x naught x minus x naught y minus y naught the whole square. I don't want to scroll off my screen there. Y minus y naught. Okay, so do you see some terms coming common? Yes, you can combine this expression and this expression. Okay, f of xy will come out common over there, so you'll get numerator is equal to denominator, okay, multiplied by f of xy, so that terms cancel out and become 1. Okay, and this will just remain here as x minus x naught alpha 1 y minus y naught alpha 2 plus 1 times f of xy. Okay, add these two terms up, f of xy comes out common, right? Numerator becomes x minus x naught the whole square plus y minus y naught the whole square, which is same as the denominator, so they cancel and give you this one, and f of xy which is taken common will remain as it is. Okay, so this is what you get, right? So we are very close to what we want, but what we have done here is we have said that the statement is true. What I have written here is true for xy not equal to x naught y naught. What will happen to this statement? What will happen to this statement when xy is equal to x naught y naught? Let us just substitute and see what happens. Substitute and see what happens at x naught y naught. At xy is equal to x naught y naught. Okay, this is going to be 0, so 0 times f1 of x, 0 times f2 of x naught y naught, 0 times alpha 1 on this side plus 0 times plus 0 times alpha 2 over here plus capital F of x naught y naught. Okay, still we are not done. What is going to be capital F of x naught y naught? The LHS over here is turning out to be 0. Let's go and see equation number 2 which we have mentioned above. Please refer to equation number 2 above. We have defined what is capital F. Okay, so LHS over here turned out to be 0. Here only f of x naught y naught survived, so that will become f of x naught. Just refer to equation 2 of x naught y naught minus, I am substituting xy as x naught y naught. So again this was already x naught y naught. Next the terms were there, the remaining terms become alpha 1 into 0 minus alpha 2 into 0. The brackets cancel out and this 2 also cancels out. So you have 0 is equal to 0. Okay, so this equation which I have written on top holds true even though I had started with xy is not equal to x naught y naught. It holds true for xy is equal to x naught y naught because both sides become 0, so there is an equality. Okay, it will not hold true if one side you had 5, one side you had 0 or something like that. Okay, where the equation is not true. Though we have shown that it's 0 at both on both sides, so the equation is true. So let us write down hence for all x comma y belonging to D, we have for all x y given belong to D, we have wait, this LHS has what over there? Let's start with the LHS as x minus x naught f1 of x plus y minus y naught f2 of x. Okay, y minus y naught f2 of x plus alpha 1 times x minus x naught plus alpha 2 times y minus y naught. Okay, f of xy. So this result we had shown was only true for xy not equal to x naught y naught. Then we verified it's true for x naught y naught, and hence we are writing for all xy belong to x, all xy belong to D. Okay. This had to be written over there also, no? Just a moment. For all xy not equal to x naught, just write over there belonging to D. It's not true for, it may not be true for points outside D. Okay. So now the RHS can be simplified. This is This is, I'll replace what is capital F over here. Okay, I'll just write it like this one because I have place. You all don't have place on your books, I suppose. So what is capital F? Capital F we have defined it as capital F we have defined it as small f of xy y minus y naught. Okay, so what do you see? Terms are getting cancelled. What remains here is only f of xy minus x naught y naught. Okay, so this is the result what we had to show. X minus x naught okay, so this is what we had to show in the statement of the theorem. Okay, so we can call this as 4 and this is true for all xy. We have to write data for all xy belonging to D. All this is 4 I suppose. Okay, all this is 4. So we have shown what was required over there in the theorem. We have to show that the functions f1 and f2 are satisfying this condition. So we had purposely constructed the functions f1 and f2 so that this holds true. Okay, so now what is remaining for us to do is only show that f1 and f2 is continuous. Okay, that was also the condition in the statement of the theorem, that there exist continuous functions f1 and f2 such that this equality holds true. The equality we have shown. Now we have to show that the functions f1 and f2 are continuous. Okay, okay, so let us start with the proof. To show that, we have to show that f1 and f2 are continuous. So since the functions are defined similarly now, I'll just do it in general. Okay, to show that f1 f2 are continuous at x naught y naught. That's all. Okay, that is, I have to show that fi, I'll call it fi because the result is same for both of them. Fi of xy minus fi of x naught y naught should be shown less than epsilon. Yeah, for a given epsilon or whatever. Given epsilon greater than 0, we have to show this on delta greater than 0 and all those things. Okay. There is a delta such that fi of this will be less than this. But what is fi of x naught y naught? This becomes alpha I, no? Because we have defined fi of f1 of x naught y naught is defined as alpha 1 and f2 of x naught y naught is defined as alpha 2. Okay, so we have to show only that this quantity is less than epsilon for whatever given epsilon. So now I need to do some simplifications over here. Okay, so now consider, before I get into the epsilon delta business, I want to show some inequalities. Okay, consider fi of xy minus alpha I. What is this quantity? Fi is defined as what? It's defined as alpha I plus, you either have x naught over there or y naught. So I'll just leave it as a bracket, okay, of f of xy. Okay, this is x minus x naught or y minus y naught, depending on which term you are referring to, right? And the denominator is same for both of them, x minus x naught the whole square plus y minus y naught the whole square. Alpha I, right? Alpha I will cancel, so we'll be left only with this. So I left only with this product here, this bracket term fxy So this can be written as a product of two terms. Oh, wait. This I can express as a product of two terms. One, the bracket term, okay, and one will be the fxy term. But you all will say the denominator is only 1 here. I will split it. No problem. I will split it as a root sign. Okay. So product of two roots will give you the full term, right? X minus x naught the whole square plus y minus y naught the whole square, right? And this will get split as root over x minus x naught the whole square, y minus y naught the whole square. Okay. So this will leave me with it leaves me with this thing and this thing, right? Now why I'm writing extra steps? Let's combine this in one step only. Okay, this is one term multiplied by this is another term. So now this term, I know what happens to it, right? I know that this expression, according to the formula, according to that equation number 3 on top, which I had marked over there, alright, according to equation number 3, the second expression tends to 0. Okay, as limit xy tends to x naught y naught, this will tend to 0, and this is the thing which I'll have to take care of, because if I'll have to take care of this thing. Yeah, so now let us do something for this. Note, observe rather, not note. Observe what you have to observe. Yeah, we know that we have done this in one of the examples yesterday. X minus x naught, okay, square is less equal to x minus x naught square plus y minus y naught square. Okay, this individual term is less than the sum of the squares. Okay, because this is a positive quantity which you are adding to this, so it has to be more than that. So taking square root on both sides, this will become modulus, because I don't know whether it is positive square root or negative square root. Okay, Yeah, not positive square root, negative square root, because a negative number can also take square of a negative number is also same as square of the positive number, right? So when I take square roots of squares, you have to be careful about this. So you have to write this as a modulus sign, okay? Because positive as well as negative numbers give you the same square, right? And here we'll take only positive square root. Okay. Similarly, you also have y minus y naught is less equal to y minus y. Okay. So this is done. So the moment you know this, that term over there with the bracket expression, whether it was x minus x naught or y minus y naught, divide by this x minus x naught square y minus y naught square. This is going to be less equal to 1. Okay, this will always be true whether you have x minus x naught or y minus y naught. This quantity will be less than 1 because the denominator is bigger than the numerator. Okay, so having said that, what do we finally conclude? This term is less than 1. Okay, so I can replace this with less than 1 and finally I'll get that fi xy minus alpha xy is less than this, less equal to this term. Okay, so let us write down. So thus fi of xy minus alpha I is less equal to okay, so thus this is what you get. Okay, so now next job will be to take take an epsilon greater than 0 and then we'll done with this. Okay, so let's start with the epsilon delta business. So let epsilon greater than 0 be given. Let epsilon greater than 0 be given. Okay. Okay, since this limit x naught y naught of f of x, sorry, okay, since this tends to 0, okay, even the modulus will tend to 0. This is true only for function, so this limit tends to 0. The f of x tends to 0, then modulus of f of x also tends to 0. Only if it tends to 0, you can't say this for any other number other than 0. Okay, so this tends to 0, the modulus also tends to 0, hence there exists a delta greater than 0 such that for x minus x naught less than delta, y minus y naught less than delta, okay, what we will be having? What we will be having? We will be having that modulus of f of xy. Actually, I don't need to assume that its modulus tends to 0, no? Okay, I don't need that assumption, no? That the modulus of f of x will tend to 0. Because I'm anyways getting the result, this is going to be less than epsilon. Okay, so if this quantity is less than epsilon, what can we see? Page is getting over, so I'll write it a little fast. Okay, yeah, so thus for x minus x naught less than delta and y minus y naught less than delta, okay, what do we have here? We'll be getting fi of xy minus alpha I is less equal to this modulus okay. So hence what have we shown? For x minus x naught less than delta and y minus y naught less than delta, fi of xy is less than fi of xy minus alpha I is less than epsilon, right? So hence fi f1 f2 are continuous set at x naught y naught. Okay, hence we started with the proof, started by constructing a function in the proof, and we have shown that construction works out fine. Okay, we have shown that the construction works out fine, that the functions f1 and f2 which you constructed satisfied the hypothesis of the theorem. Also they are continuous. Okay, that equation which was given in the hypothesis, they satisfied that, and also we have shown that they are continuous. Okay, and hence the result is true. So hence there exist continuous functions f1 and f2 such that equality holds true. Okay, so given a differentiable function, I can find two continuous functions f1 and f2 such that given equality, f of xy minus f of x naught y naught is equal to x minus x naught f1 times xy plus y minus y naught f2 times xy is holding true for all points in the set D. Okay, so this is done. So we are done with only half the proof. After struggling for nearly 1 hour, we are done with half the proof. Yes. Okay, so half the proof is over. So now we have to prove the converse part of the proof. Okay, so let us start with the converse of the proof. Okay. Okay, I'll write the converse on the other side because this side of the page is over. Okay, enough. So let us start conversely. Conversely, I have to assume that there are two continuous functions f1 and f2 which satisfy the condition, and I have to show that f is differentiable. Okay. Okay. So let us start with this converse of it. Conversely, conversely, let there exist f1, let there exist f1, f2, and b subset of R continuous continuous at x naught y naught. And satisfy this condition, that is x minus x naught, for all xo belonging to D. So this is done. So now I have to show that, or I rather claim, f is differentiable at x naught y naught. Okay, f is differentiable at x naught y naught. So that is, I have to show that limit of, I have to show equation number 3 on top is true, that is xy tending to x naught y naught, f of xy, this quantity is equal to 0. Okay. So where f of xy is defined as before, it's what we have defined in the original part of this proof. So let f of xy be defined as before. What was that anyways? Even I forgot. So let me write down again. It's f of xy is equal to, we refer to the book. What was it? Yeah. Sorry, should have been y. Okay. Only thing we have to change the definition of f1 and f2 now. Oh, I have to define alpha 1 and alpha 2, where alpha 1 is defined as this number x naught y naught, and alpha 2 will define it as this number f2 of x naught y naught. Okay. X2. Okay, so this will be x2, yeah. This will define yeah, so this statement is true for all xy belonging to D. This above one. Okay, yeah, x comma y in bracket. Okay, so that is done. So let me just simplify this expression now. Yeah, we have assumed this statement, right? We have assumed that f of xy minus x naught y naught, f of x naught y naught is equal to this. So I'll substitute over here. Okay. Here also I have this, right? But I've said this f of x y minus x naught. We will give a number. 4 I have used a bonus, so let's call this as 5. Call this as equation number 5. Call this as 5. Okay. Next, call this as 6. In case I've already used 5 and 6 before, then just write the number next. Don't distinguish. Okay, instead I've already defined 5 earlier, then write that as 6 and this as 7. But I doubt I have done that much. Okay, never mind. So substitute 5 in 6. So what will be left with? We'll be left with f of xy is equal to that expression there. This is alpha 2 times y minus y naught. Okay, and this statement is true for all xy belonging to D. Okay, for all xy belonging to D, the statement is true. Okay, so we'll simplify this expression a little more. You can see that we can take out x minus x naught common. So write down x minus x naught common. What we'll be having there is xy minus alpha 1 plus y minus y naught. Okay, f2 of xy minus alpha 2. Okay, what I'll do next is I'll divide both sides by root over. This is true for all xy belonging to D. This is true for all x comma y belonging to D. Okay, so divide both sides by root over x minus x naught plus y minus y naught the whole square over here. Divide both sides by this expression. Why am I doing that? Because I have to take limit of f upon this, right, as x tends to x naught y naught. Okay, so thus for all xy belonging to D, now xy will have to ensure that it is not equal to x naught y naught, because I have put this term in the denominator. We have okay, this is equal to this is equal to x minus x naught bracket plus y minus y naught f2 of write it as two separate terms. Okay, so we reached here. Now we are almost done with the proof. Okay, so what we are going to do next, take modulus on both sides. Okay, take modulus on both sides, then use triangle inequality. I'll just write in brief what is to be done now. This is going to be modulus of this expression. Applying triangle inequality, you will get modulus of this big expression plus modulus of this expression, but then you split it up as two moduluses. Okay, modulus of this bracket term divided by the root sign, and outside you keep modulus of f1 xy minus alpha 1 plus again the same thing here, the bracket term divided by root sign, and the second modulus will be f2 minus alpha 2. I don't have place to write all these details, right? But what do you know about this? The bracket term divided by the root sign, the modulus has to be less than 1, right? We have already shown this above. Okay, this quantity will be less than 1 because the numerator is less than the denominator, right? I'm getting the modulus, that's why it's less than 1. Okay, so that modulus is less than 1. So finally, after doing all this, what we are ending up with is f of xy, sorry, write the full thing and then take the modulus, huh? Otherwise it won't fit inside. X minus x naught okay is less equal to f1 of xy minus alpha 1 plus f2 of xy minus alpha 2. But what is alpha 1 and alpha 2, by the way? This is nothing but what we have defined alpha 1 and alpha 2. This is f1 of x naught right. This is our definition of alpha 1 and alpha 2 in this part of the proof form. Just read and see above. Okay, this is equal to this, right? But what do we know? f1 and f2 are continuous functions. Okay, so hence let epsilon greater than 0 be given there exists a delta greater than 0 such that for x minus x naught less than delta and y minus y naught less than delta, there exists nothing more direct system. Okay, for this expressions we'll be getting f1 of xy minus f1 of x naught y naught okay, this is going to be less than epsilon by 2 and also the other one is going to be less than epsilon by 2. Actually the same delta need not exist for both of them. If you solve this problem in details, you'll realize that given epsilon greater than 0, there will be existing a delta 1 here and there will be existing a delta 2 here. So our delta over here has to be the minimum of delta 1 and delta 2. Okay, so those details I won't get into because I assume you'll understand all these things by now. Okay, but yeah, so these two quantities are less than epsilon by 2 and hence hence actually this is true, right? Because x is not going to be equal to x naught. So this statement is true here by putting a greater than 0. Okay, we can put a greater than 0 here. Here it was not required for this continuity part, but for this part I require it because I want to ensure that the denominator is not going to be abnormal. Okay, and 0 is less than y minus y naught. Okay, yeah, it is true anyways because we have stated on top that we are taking x comma y belonging to d such that x comma y is not equal to x naught y naught. Okay, so for that reason this statement is going to be true. This is somewhere here I had said that before dividing. Yes, if for all xy belonging to d and xy not equal to x naught y naught. Okay, so because of that reason I can take this. Even here you could have taken it, we didn't need it, but for this limit we require it. Okay, so for this expression this f of xy upon this okay, this I can write minus 0 is less than epsilon by 2 less, okay, minus 0 has no meaning ever. I purposely put it in so that I can finally conclude that limit of, it's a valueless quantity, right? So I can add by 0, subtract by 0. Okay, so without changing the value of this expression. So that's what I did. Why I did it? So that I can claim that of this expression, this is equal to epsilon. This is equal to 0. Okay, and what happens if this particular limit is equal to 0? We have defined capital F to be the numerator of that definition. Okay, this implies that limit of, that is, there exists alpha 1 alpha 2 belonging to R2 such that this limit okay, this limit is equal to 0. So what do we conclude from this? This implies that f is differentiable at x naught y naught. Not only that, not only that, we have also concluded here that the way this construction was done, also because we had said in the definition of the derivative that this alpha 1 and alpha 2 have to be nothing but gradient of f, right? So gradient of f is going to be, but we have taken alpha, is going to be alpha 1 and alpha 2, but we have taken alpha 1 and alpha 2 to be equal to f1 of x naught y naught and f2 of x naught y naught. Okay, so this is the end of the result, but we have to still make some notes here. How long did it go? 1 hour 24 minutes, but we're still not done. We have to just make some observations here. Okay, so this page is as good as over. Okay, there's lots remaining to this page. Okay, so let us write here. Okay, so this is the end of the proof. So just write QED, the end of the proof. For those who don't know, this stands for coordinate discrepant. I told the other day. Okay. It's a Latin word. It is. In English, it translates to what was asked for. Okay. So basically, it means the end of the proof. You had asked me to prove this, so I proved this. That's what it means. Okay. Yeah. So just some notes here. The pair of functions, the pair of functions f1, f2, okay, satisfying the increment lemma, capital I will put, increment lemma satisfying the increment lemma are called a pair a pair of increment functions associated with f at x naught y naught. Okay, at the point x naught y naught. Yeah, if you change the point, the functions might change. Huh? Okay, the increment functions might change if you change the points of your x. If you change the point x naught y naught, your increment function might change, because if you notice, the function was constructed using the f1 and f2 were constructed using these things. Okay, it had that x minus x naught term in that function. It was alpha 1 plus x minus x naught times capital F divided by that quantity, and it was alpha 2 plus y minus y naught times capital F for the second function. Right, so if you change your x naught and y naught, the functions might change, but in certain situations they won't. Okay, yeah. Another thing which you should have noticed here, I used the word a pair of increments functions. I didn't say the pair of increment functions. So obviously what I'm trying to say here is they need not be unique. Okay, increment functions for a given function at a given point need not be unique. I'll show you some examples down after some time. Okay, so another thing is, this is a local behavior of the function. Okay, now the page is over. Okay, let me write sideways here. Okay. Okay, so just note here is that differentiability is a local property observe, or just note differentiability is a local property. It's a local property, okay, or local condition, you can say. If it is true at one point, it need not be true in other places of the what do you call that? It need not be true at other places in the given domain. Okay, there are some properties which are true at one point and they easily follow for the neighborhood of that point and so on. Okay, so but not about differentiability. Differentiability, if it is true for one point, it may not be true at some other points in the domain. Let me elaborate on what I mean by this. Actually, it's not just applicable to f, but even to f1 and f2. Okay, so if d is a subset of R2, okay, and x0 y0 is an interior point of D, okay, then what will happen? This implies there exists a delta greater than 0 such that S delta of x0, there is an open ball or an open square in this case about x0 y0 which is contained properly in D. This is the definition of interior point we had seen earlier in this course, right? So now if this is an interior point, then you can find this, right? So now then f is differentiable at x0 y0, if and only if the restriction of a function to S delta x0 y0, okay. What do you mean by restriction of the function f? The function f is defined on a big domain. We just consider the function on the smaller domain. That's called as restriction, right? The restriction of right f, restriction of f is restriction of f to S delta x0 y0 subset of D. Okay, if and only if this restriction function is differentiable at x0 y0. Okay, the original function is differentiable if and only if the restricted function is differentiable. But what's the use of this restricted function being differentiable now? What's the use of this restricted function being differentiable? If the statement is true, hence to show f is differentiable at x0 y0, we only need to find f1 f2 on continuous on S delta x0 y0. Okay, continuous on x delta x0 y0 for some delta greater than 0. Okay, so see, the problem was to show a function is differentiable, I had to find f1 and f2, right? So here, because this local property is there, that if it is true on a bigger set, it's true on that local open neighborhood over there, right? So what I'll do, I'll actually only find f1 and f2 on which are continuous on the small neighborhood over here. That is much easier to find. It's very easy to find a continuous function on small sets than a continuous function on the bigger set, right? Okay, so the smaller your set, easier it is to find a continuous function on that smaller set. Okay, bigger the set, it will become more and more troublesome to find continuous functions which are satisfying that condition. It's not arbitrary continuous function, they have to satisfy that condition over there, right? So they are continuous on this small delta neighborhood over there, and satisfying the condition f will be differentiable. The restriction function fs delta will be differentiable, but if the restricted function is differentiable, the original function will be differentiable. Okay, so hence the result. Alright, now for the next thing, next observation. Yeah, this is a more important one. The second one is increment functions are not unique. Second observation, the pair, second note I think so I called this, the pair of increment functions are not unique, are not unique. Okay, so let us just see this with an example. Let f be a function d to r be differentiable okay, and f1 f2 be the pair of associated differentiable functions, associated increment functions not differentiable. Okay, f1 and f2 put in a bracket. Now we define g1 g2 from d to r as follows. As follows. Okay. Okay, so we'll just need something extra here. For any continuous don't say for any, I'll say let only. Let h from d to r be continuous okay at x naught y naught. Okay, h can be any function, h can be any function, no restriction on that. Okay, so for this it can be any function which satisfies the continuity at x naught y naught. Other places what it does I'm not so interested in. So yeah, so what we do is we'll define this here. Wait a minute. Okay, wait a minute. Yeah, so what we're going to do is, yeah, we're going to define g1 of xy g1 of xy as f1 of xy plus y minus y naught of h of xy. Okay, and g2 of xy of f2 this will become x minus x naught of h of xy. Okay, so then g1 g2 is also a pair of increment functions, associated with uh, increment functions of a pair of increment functions okay, page is over, I move slightly left, associated with f at x naught y naught. Okay, so this becomes another pair of increment functions at x naught y naught, right? So continuity at x naught y naught follows obviously because we have taken g1 and g2 has to be continuous at x naught y naught, right? So that is very clear because f1 is continuous at x naught y naught. Y minus y naught is a polynomial expression. It will be continuous at x naught y naught, and h is also given to be continuous at x naught y naught, right? So this combination will be continuous. Same for f2. F2 x minus x naught and h of xy, all these things are continuous at x naught y naught, and hence g2 is also continuous at x naught y naught. Okay, so let me move a little left. Only thing what I have to prove is that they satisfy that condition over there, that f of xy minus x naught y naught is equal to that thing, is equal to x minus x naught times that. Okay, just a minute, I think so I made a mistake here. Sorry, this was wrong. This had to be minus. It's clear that they actually satisfy this thing, but I'll just show you. Okay, I have to show that they satisfy that condition over there, right? So consider x minus x naught times g1 of xy plus y minus y naught, okay, times g2 xy. Okay, but what is g1 and g2? This is going to become equal to x minus x naught times f1 of xy, that's already given to you. Next, yeah, plus term was there with this, right? So that is going to become, there you have y minus y naught. So this will become x minus x naught into y minus y naught h of xy. Alright, and the second term is going to contribute over there. I'll write it down now. Y minus y naught times f2 of xy minus sign is there. So this will become y minus y naught of x minus x naught h of xy. As you can clearly see, what remains here is only this much. Okay, but what is this equal to? This is equal to nothing but f of xy minus f of x naught y naught. Okay, so to be an increment function, your functions, a pair of increment functions, your functions h1, g1 and g2 have to be continuous at x naught y naught. That I told you is very obvious, and they have to satisfy this equality, right? That this combination of them should be equal to f of xy minus f of x naught y naught, which is also true. Okay, so hence g1 and g2 are increment functions. g1 g2 are a pair of increment functions. Increment functions of f at x naught y naught. Okay, so at a given point, how many such functions can you find? Infinitely many, because h can be any continuous function, right? So how many continuous functions are there at one point? Infinitely many. Okay, so you'll find infinitely many continuous functions also at that point. Okay, so the pair of increment functions are not unique. Okay, you can find infinitely many of them. Okay, so let us finally wind up over here with some examples of increment functions. Okay, this I'll do in the next video only. Okay, because this video became too long. It's already 1 hour 47 minutes over here. Okay, so we'll stop with this theorem and the proof of it. Okay, so in the next video I'll do some examples on increment lemma, and then I'll do the reason why we studied increment lemma, that is to show that every continuous function is every differentiable function is continuous. Okay, yeah, that proof is only going to be 4 lines. Okay, so after studying one proof which took us only almost 1.5 hours to prove, we're doing a result main theorem which will be only 4 lines long. Okay, so that's the reason why we study lemmas. We study a difficult lemma so that our main theorem becomes easy. Okay, so that's all in this video. Thank you for watching. Bye bye. Yeah, one more thing, just watch this video in parts, otherwise it will be too heavy to watch. I told this at the end of the video. How you'll know? Never mind, I'll have to give it in writing before. Chalo then, bye bye. I'll message in the group too.